Good afternoon. My name is Mohsen Beatty, and I'm the acting dean of the College of Earth, Ocean, and Environment at the University of Delaware. I'm so happy that you have all chosen to join us. Oh, sorry. I'm so happy that you have all chosen to join us as we welcome two special guests to the university, Dr. Walter Munk and Mr. Chris Mooney, as we celebrate Earth Month and we collaborate with the Institute for Global Studies to recognize the university's work in the Arctic. As a college, we trace our roots from inception as a marine program at UD in 1951 to the 1970s when we were the Graduate College of Marine Studies, to 2006 with our growth to the College of Marine and Earth Sciences, and finally through today as the College of Earth, Ocean, and Environment. Our commitment to issues at the forefront of balancing the environment with the society has been steadfast for decades, and we continuously look for new, innovative ways to teach students and our future workforce, conduct meaningful research, and guide policy that will enhance economic development while sustaining our planet. To introduce our guests today, I welcome UD Acting President Dr. Nancy Target to the stage.
Thank you all, and I'm really pleased to be here today. It's a pleasure to introduce our guest speaker for today. And for those of us that are in the field of oceanography, Dr. Walter Munk really is the quintessential person who needs no introduction. His lifetime of pioneering research, his passion for teaching, and really the many accolades that he's received over his career really do make him no less than a legend. And it's no exaggeration to say that you built and shaped the way we study and understand the oceans today. I had the pleasure, along with a number of others, of having lunch with Walter and Mary today, and to welcome into the home at 47, into the President's house at 47 Kent Way, and to hear the stories and the richness and the texture and the fabric of his life and their lives together is really wonderful. So we're in for some real treats this afternoon. I do want to highlight some aspects of Dr. Munk's life and distinguishing career. So Walter Munk was born in Vienna, Austria in 1917, and he emigrated to the United States in 1932. Some would say he was sent here because he was skiing too much in Austria, and his parents wanted to make sure that he had a little bit more discipline. So in fact, he did. He was put into a school where that was the case, but then he went ahead and organized a ski club anyway. And that was around the age of 15. When he was at Caltech, he earned a bachelor's in applied physics in 1939, and then in 1940, his master's in geophysics. It was in 1945, before most of us were even born, that Mr. Munk became Dr. Munk, and he earned his doctoral degree in oceanography from Scripps Institution of Oceanography, which is at the University of California at San Diego, and really was a seminal individual and very important in the early days of the founding of Scripps and really the founding of UCSD. Throughout his career, Dr. Munk has contributed to both the fundamental science and practical applications of oceanography, and you see that a lot in ocean science. It's that continuum of fundamental understanding leading to application. And he and his colleagues from Scripps developed amphibious warfare methods at the U.S. Navy Radio and Sound Laboratory, and this included wave prediction methods that were used during the D-Day invasion of Normandy. He studied ocean sound transmission, deep sea tides, climate change, ocean currents, and wave propagation. Dr. Munk helped establish the Cecil H. and Ida M. Green Institute of Geophysics and Planetary Physics at Scripps, and that's a center that has produced many leading researchers in seismology, geomagnetism, and other Earth processes. His work on the mid-ocean dynamics experiments, that's called MODE, in the 1960s and 70s significantly improved the accuracy of tide prediction. And it was interesting for me because as a beginning grad student at the University of Miami, I worked at the Atlantic Oceanographic and Meteorological Laboratory there in the mid-70s, and I remember participating in the mode cruises, and one of the people that I worked for was someone who was working on those deep-sea tides. By 1975, Dr. Munk was experimenting with using sound waves to generate images of the ocean. This is known as acoustic tomography. And in 1991, he was part of that experiment that was called the Sound Heard Around the World. And it was one in which they demonstrated that long-range, low-frequency sounds that were generated in the southern Indian Ocean could be heard thousands of miles away in Bermuda. 10,000. 10,000. I was off by an order of magnitude. Throughout his career, he's been recognized with some of the highest honors in the field, including the Alexander Agassiz Medal, the National Medal of Science, the William Bowie Medal, the Vetlesen Prize, the Kyoto Prize, and the Crayford Prize. Here at UD, Dr. Munk was part of a review team that helped establish the Physical Ocean Science and Engineering program that is in the School of Marine Science and Policy. And that program is designed to provide students with a strong foundation in physical oceanography, as well as opportunities to acquire state-of-the-art observing and modeling skills while working closely with faculty. These days, Dr. Munk, at the ripe young age of 98, continues to conduct research as an emeritus professor of geophysics and the Secretary of the Navy Chair in Oceanography at Scripps Institution of Oceanography. And at the conclusion of his remarks, he'll be joined on stage for, I think, if lunch is any kind of an introduction to this, to what will be a fascinating discussion with journalist Chris Mooney, who's joined us. Chris covers energy and environment for the Washington Post, and they'll be doing a back-and-forth interview. So with that, please join me in welcoming Dr. Walter Munk. Thank you.
Well, thank you. Thank you, Mosen, and thank you, Nancy, for your kind words. I've been here 3 times. This is my 3rd time. 1998, 2002, 2016. I noticed that in 2002 I was given 45 minutes, and today I was given half an hour. So you're making sure that I don't go on forever. Let me show you the first slide, please. It's not very visible, is it? But it's my visit last time. And there are quite a few people on this slide who are here tonight. And I welcome being able to come again very much. The next slide shows what I'm going to talk about. The assignment I had from Mosen was to talk about climate change, but climate change from the point of view of how it interacted with my own work. And I very welcome that assignment. And you know, people generally equate climate change nowadays to the CO2 problem, to the increase in CO2 energy with time. But I want to emphasize that there was a lot of work done before then. And that work is still important, and some of it is still unsolved. You see here the various planets orbiting around the sun, and what I'm going to talk about for a while is the perturbation of the Earth's orbit by other planets, particularly by Jupiter because it's so big, and by Venus because it's so close. And there are two kinds of orbital perturbations which are particularly important. The angle between the solar plane and the equatorial plane, now at 23.5 degrees, is known as the obliquity. It's 23.5 degrees. And it has a perturbation changing remarkably much from 24.5 to 22.5 degrees in 41,000 years. And when it is at the lower number, 22.5, very little of the solar radiation reaches our high latitudes, and we have an ice age. And when it's at the higher figure, 24.5, you have major melting, major changes in sea level, and today we happen to be just about at the middle, 23.5, but in 10,000 years, it'll be at 22.5, and we will have another ice age unless we do something about it. The other change is the eccentricity. How elliptical is the orbit? That is a more complicated perturbation, but let's say it has an effective period of 100,000 years. And it changes all the way from 6 degrees to essentially a circular orbit, zero eccentricity, with this period of 100,000 years. And these two important changes have been studied by a Yugoslavian oceanographer, Milankovic, and did lots of very good work, he and others, before CO2 ever came up for consideration. Next slide, please. And that was Milankovic, and the attempt, and you can read what it says about his theory. He did a good job. Thank you. Next slide. Now here is a remarkable result of work that's been conducted in the last 10 years under the leadership of Severinghaus at Scripps. And it's making ice cores in the Antarctic and then examining those ice cores for little air bubbles at various times. And those ice cores have essentially now an age up to 600,000 years. And they are working to extend it to 1.5 years. And the 3 slides you see, the upper one is CO2 as measured in the bubbles, or air bubbles, that are found and dated in those ice cores. They have a diameter, something like this. The next one are the measured CO2 content. Oh, I have that wrong. The upper one is CO2. The second one is temperature in degrees centigrade. And the third is an independent collection, not in the Antarctic, from CO2 at the same depths. And you see they extend to an age of 1.5 million years. And now notice something very strange. About 1 million years ago, where the arrow is pointing, before then, the temperature variations had generally periods of 41,000 years. Before then, the last 1 million years, they have variations that are more consistent with 100,000 years. And no one knows what happened at the time to bring about this change. And those are the collection of those cores are a wonderful accomplishment in telling us something about the past orbital perturbations of the Earth. Next slide, please. Now, you've seen this slide ad infinitum, ad nauseum, I would say. This is the Keeling, famous Keeling slide of CO2. And you see how very much CO2 has increased from 1960 until today. And we've all seen the slides. I want to point out for your own calibration that during the warm periods, it was lower than the lowest numbers here, more consistent with 280 parts per million. And during the ice ages in the past, it was more consistent with 180. No, I can't read that, 180. So there's a very, very significant change in CO2 in the last few years. Now, can I go back one, Mary, please? Go back to the 7. Yeah, no, back one. One beyond that. No. Next one. This one. There are two things I want to point out about this slide that are extraordinary. One I already mentioned, the change in the historic temperature about 1 million years ago, which is not understood. Then in the upper slide, do you see the very steep extension going upwards from now? That's the measured CO2 in the last 60 years from the work of Keeling. Precipitous rise, totally inconsistent with the natural variations that happened before then. And I want to point out that in the past, the temperature led in phase with the CO2, meaning that temperature variations caused the CO2 change in the atmosphere. But in the last 60 years, with the enormous change in CO2 by human activity, the CO2 has led the temperature and is responsible for the temperature changes. And I think that's all fairly well understood. Now, when I first came to Scripps in 1939 as a junior from Caltech, we had just found out that the CO2 was beginning to rise, and a projection of the natural pattern would suggest, as I mentioned, that we're moving towards an ice age. And everybody was congratulating themselves, weren't we smart to have the CO2 warm the atmosphere to make the coming ice age less severe. And the only trouble is we've overshot by a few order of magnitudes. But I do want to say that's really the key of what I want to eventually leave with you, namely that there is a chance with CO2 or other means to mitigate the natural change. And I think that'll be a challenge for oceanographers of the next generation. The next curve, Mary, which we had before, has one lesson, and the lesson is that if you want to make measurements that are significant for understanding climate change, you have to do more than 10 years. You really should do a century. And how did we get about having such a long measurement? Well, Ralph Keeling was an unusually stubborn person and just didn't permit the agencies that supported his work to stop. We can't depend on that in future. We need to have some assurance that climate measurements can be done for something of the order of many decades. And in 1995, Vice President Gore, G-O-R-E, who had been a student of Roger Abels at Harvard, started a CIA agency called MEDEA, now totally unclassified, and for the purpose of measuring the Arctic and other climatological measurements, with the idea that the changing climate was a factor in US security. And the problem came up even then: how can we be sure that some of these measurements are carried out for many, many decades? And there were various suggestions, but the political time constants of the United States, 4 or 8 years of presidential service, are not very helpful for climate work. They aren't long enough. And nobody knows the answer until now. But a very curious thing happened. When Gore was defeated in the year 2000 and Bush came in, it was clear that nothing that Gore had done would be continued. And so the MEDEA committee went into a hibernation. We thought it was discontinued for 8 years. And then to our amazement, we all got a message, all members of the MEDEA committee, saying, we're meeting again next week in Washington. And we met next week in Washington, and it turned out the CIA had continued to take all the measurements that we had requested. Somebody forgot to turn them off. And so we have a simple answer how to get long-term measurements for climate purposes. You ask the CIA and forget to turn it off. Now, when I came to Scripps in '39, Harold Sverdrup, the famous Norwegian oceanographer, was director. And I had a wonderful summer. I was a junior working there. Harold Sverdrup lived on the campus, and he had been a gymnast, and he would entertain us with standing on his head for 5 minutes. And I proposed that all directors of oceanographic institutions should have the ability to stand on their head in 5 minutes. And he also had come back from 7 years in the Arctic and told us that he was very uncomfortable about not understanding the processes at the bottom side of ice sheets. How do they melt? How do they interact with an ocean? That was a problem for the future. And it came up many, many years later that we really did not understand the processes, and we still had to learn about them. Well, I came back a year later in 1940 and decided I wanted to become an oceanographer. I had by then graduated from Caltech, and I asked Sverdrup whether he would take me as a student. And I well remember 10 seconds of silence, the longest 10 seconds of my life. And then he said, well, I would like to consider that, but I cannot think of a single job that will open up in oceanography in the next 10 or 20 years. And I quickly said, I'll take it. And what happened is at the time, the only jobs in oceanography were at Scripps, at the University of Washington, and in Woods Hole. And we had to wait until one of the professors died until you could possibly get a job. Well, I accepted it, but then at that time, the Germans were overrunning Europe. My country, Austria, had been invaded. I was very much involved very worried about that. And I joined the US Army, took advantage of my skiing, and became a member of the Army ski troops, and served for 18 months. And then Sverdrup and Rebel and others started a new study for the University of California, requested by our president of the university, for learning something to combat the fact that German submarines were sinking Allied shipping at an unacceptable rate. And they requested my discharge. I had served long enough, and I joined that group and got engaged in ASW, anti-submarine warfare. Now, a week after I had left the Army, Pearl Harbor happened. All leaves were canceled. My group was sent to Papua New Guinea. Papua New Guinea was virtually wiped out. And I started working at the US Navy Radio and Sound Laboratory on anti-submarine warfare problems as a civilian for the Navy. A little later, I found myself assigned to the Directorate of Weather of the Air Forces in the Pentagon, and was privileged to observe a landing exercise in the Carolinas using LCVPs, landing craft vehicle and personnel. The Allies, were planning the first Allied initiative, not in response to Axis initiatives, to be a landing, an amphibious landing in Northwest Africa in late 1940. I witnessed the landing exercise in the Carolinas. Anytime that the waves exceeded 5 feet, the breaker height exceeded 5 feet, the landing craft would broach, turn parallel to shore, waves would break into it, people would get hurt, and it was decided then to postpone any further exercise until some future day when the waves were lower. Well, I went back to the Pentagon and tried to find out from various literature what the expected wave height would be, breaker height, in Northwest Africa in winter, and found that estimates would be above 6 feet. So it seemed to me there was a catastrophe about to happen, and that the only way out would be to learn to predict waves so that you could choose a good landing day. There had never had been a wave prediction before that time. Of course, they're so commonplace today that you can pick up your wave prediction for a week in advance by just turning on your television set. Anyhow, I went to my commanding officer and said, we have to learn how to make wave predictions to be able to pick a good day for the Northwest Africa landings. And he said, Munk, go back and do what you're told. I had no presence to speak of. And I was really very worried, and I called up Sverdrup, my director at Scripps, and said, please come to east, and he flew out the next day. And we spent a month in the Pentagon seeing whether it would be feasible to predict waves. And we called our effort Sea Swell Surf. Sea for predicting the waves that leave the storm area depend on wind speed and fetch. Swell, what happens to the waves in what may be a considerable distance between the storm area and the landing beaches. And surf, how the waves would be modified in shallow water, the more difficult of the three. And with Harold Sverdrup's prestige, we did persuade the authorities that we should learn how to and teach Army and Navy meteorologists to predict surf for forthcoming amphibious landings. And we held classes at Scripps, generally lasting a month, and generally having a dozen officers. And all I remember is that at the end of the first month, the first class, we tore up all our notes and started from scratch for the second month, et cetera, et cetera. I forgot to tell you that we had, in fact, Harold Sverdrup and I predicted the landings for Northwest Africa, and it turned out to be a fairly calm day, but one with very considerable Vichy French opposition. But more luck, I think, than ability. But these classes of 100 or so officers did all the predictions for the Pacific theater of war against the Japanese. And as a whole, they worked very well, with the exception of the landing at Tarawa, where we got the tides wrong, led to very bad losses. And then two of these officers predicted the landings in Europe, the Normandy landings, which were initially predicted to be impossible because of bad wave conditions, which Eisenhower postponed for 24 hours. For the next day, the prediction was difficult but not impossible, and he decided to land. And as it turned out, it was a very difficult landing. And the following thing had happened. The German prediction, the Axis prediction, had said that it would still be too difficult to land on the second day, and so the German defenses had essentially been very much diminished, partially withdrawn. And as it happens, the German prediction was better than the American prediction, which was a good thing because it was easier to put up with difficult waves than with armed resistance by the Germans. And so the landings took place in the early morning, very heavy losses until German defense was put away. And the incredible result, by the end of the first day, the Allies had landed on 3 adjoining beaches, 150,000 people, with some heavy losses, but nonetheless successfully. The incredible thing that I want to remind this audience of is that 3.5 years after the initial landings we had studied, 3.5 years after Pearl Harbor, starting with a losing difficult situation, we landing in Normandy, and the war was soon ended. For me at least, these years were very happy years. Everybody worked together. It was incredible what could be done with everybody working together. And we started from a very negative situation to a dominant situation in just 3.5 years. There is now a U.S. committee, UC committee of all 10 UC campuses to make the University of California, my university, carbon neutral in the next 10 years. And it seemed like a very difficult problem, but it seemed equally difficult after Pearl Harbor to do something about the ASW, the Axis ASW. And I'm just hoping that we have equal success. I should say that before Pearl Harbor in 1941, the Scripps students and many other students didn't know where they're going to work after they graduate. And 3 months after Pearl Harbor, the jobs were looking for students. It turned out there was such an enormous demand on the ability. And I expect this might happen again on the present climate problem. Anyhow, now let me look at the next slide, please. And I want to tell you a little bit about our work. This is a famous picture drawn by the German philosopher Kant several hundred years ago. Look at the upper figure. The black area is a high tidal area from elementary theory, and there's a protuberance on the lunar side and on the anti-lunar side. Why are there two high tides if there's only one moon? Well, the nearby ocean Earth is pulled away from the center of the Earth by the moon, and the center of the Earth is pulled away from the far area, so you get a high tide on both sides. Now, that was known for a long time, but it was found from observations that global high tides lag high moon, as shown in the lower slide. Notice that the high tides are plotted here with some lag, both the nearby and the far side. And since the near one, maybe you could I point this, no, the near high tide, the black area, Barry, at the Earth, is closer to the moon than the far one. The moon exerts a stronger pull on the near tide than the far tide, and that slows down the rotation. And I'm showing this tide to say a very funny thing happened when we started to study the tides. It turned out, first of all, a solar eclipse is a very accurate measurement of positions of high and low tide, because by strange accident, the lunar angular size is very nearly the same as that of the sun. So the eclipse is a statement, a very accurate statement of the positions of the moon and sun. And the eclipses have been predicted for many hundred years with some accuracy. And it turned out that they happened at the predicted times very well, with one curious situation, namely that the places that were predicted, the positions on the Earth where they were supposed to be visible, turned out to be wrong. A prediction for a solar eclipse for London was actually seen in Babylon. And the only explanation seemed to be that the Earth's angular velocity, the length of day, was not constant, because the prediction had nothing to do with the position of the Earth's rotation. And when the different eclipses were examined, allowing for the fact that the spin of the Earth could diminish, but it turned out that it could be decided, it could be calculated what the deceleration would be. And it was such that the length of day was increasing 1 millisecond per century. 1 millisecond per century to account for where the solar eclipses were observed. And that doesn't seem like much of a slowing down, but in 10 million years, that means the length of day is 3 hours longer than it was before. And so eventually, in fact, the Earth will stop spinning like the Moon, and some preferred lucky area of the Earth, not yet determined, will be turned towards the Sun, and some area on the other side will be in eternal darkness. So anyhow, it was that work which made me go into studying tides, and we were blessed at the time in having several new developments. One was that Frank Snodgrass of Scripps had designed an instrument that could be tossed over the side, sink to the sea floor, maybe at great depths, 5 kilometers, record pressure against time, and after a month or so, the instrument could be recalled by acoustic command. So we had, for the first time, the ability to measure tides, not in harbors where it was available from tide gauges, but anywhere in the open sea where we wanted to see them. And the second new development was that the emerging computer ability made it possible to do theoretical calculation of tides for actual ocean boundaries. In the previous century, George Darwin, son of Charles, had been working on tides in theoretical basins of simple shape, like circular basins or rectangular basins, but those were of little use. So now we had the ability to calculate what the tides should be anywhere in the open sea and to measure it. And so when I requested National Science Foundation to support us in making a global attempt to understand the tides that were associated with the changes in angular velocity, they wrote a letter back, said, didn't I know that tides had gone to bed with Victorian mathematicians? And I said, no, I didn't know that. Anyhow, we eventually got supported, and we spent 10 years measuring about 100 deep-sea tide stations, we being Dave Cartwright from Britain and our group at Scripps. And at the end of that period, we had a pretty good idea about global tides, which was not possible when measurements were only taken in harbors and things. So then the question was, what causes the slowing down of the spin due to Earth tides, due to tides. And turned out molecular viscosity, as always, was entirely inadequate. And so we had to learn how tidal energy was dissipated. And G.I. Taylor, English geophysicist, had done the first decent estimate by learning how to compute the dissipation of energy in a flow on the sea floor, a drag coefficient times rho u cubed, and he actually checked out his work by measuring the flux of energy in and out of the Irish Sea to get a balance between the measurements and the theory. And so we started to have a beginning of global tidal friction, and it still wasn't enough to explain the rate at which the Earth was spinning down. Then came the realization that barotropic tides, surface tides it is, are scattered into internal tides at features such as the Mid-Atlantic Ridge and a similar feature in the Pacific. And the internal tides are highly dissipated because of their increased shear. And so we could get new measurements or new estimates of global tidal dissipation. And eventually the budgets were determined. And as a byproduct of that, we learned something about deep ocean mixing, which is due to the internal tides and has now a large number of people who are working on that problem. Anyhow, I want to just leave you with the fact that this attempt to understand global tides, it took a lot of my career and closely related to trying to understand the variation in climate. Well, I think I should come to some sort of a conclusion. Let me try and say a few words in conclusion to the climate problem and what will or may happen to it. Oh, there's a famous, please show the next one. When we worked on tides, we found, of course, that the moon is the important one in causing tidal friction as compared to the sun in a ratio of 5:1. And we picked up, we being Karl Wunsch and I, a Russian comic strip called, what's his name? Yeah, unpronounceable. He was a private in the Tsar's army, and he was very dumb and didn't know what he was talking about, but he always got things right. And so somebody asked him, what is more important, the moon or the sun? And he said, the moon, of course, because the sun shines only in the daytime when it's bright anyhow. And Karl Wunsch and I published our work on tides, and we called it The Moon, of course, and showed these figures. I should mention in closing comments about our work on tides that we had a funny experience that some of you might have when you learn new things. When we first claimed that the deep ocean is mixed by internal tides, we had one reaction: you're wrong, it's a mistake. And 20 years later, that had changed to everybody knows that and it's obvious. So don't expect any any glories when you have a really new idea. It may survive for 20 years, and you will go from you're mistaken, you're wrong, to it's obvious in a few decades. Well, let me try, and that is the last one.
There's one more.
One more. Oh, we already had that. Oh, no, I'm coming to that. Don't show it yet. I'm sorry. Let me try and summarize a very difficult subject in as few words as possible. The oceanographer's job is to understand and predict tidal change. And that's something that all of us have worked on with variable success. The other job, to adapt to the changing climate and to mitigate it, if possible, to make it less severe, is much more difficult than the oceanographic job to understand and predict. Even if that is very hard, it's much simpler than the requirement to adapt and mitigate. It's made difficult by the multinational nature of being able to mitigate and adapt, especially since adaptation will be different in different countries, and they may want different kinds of response and different tides. So the present challenge is that we need to adapt to sea level rise in about, that will take place in the next 100 years, century. And as far as I know, there is no good solution to that adaptation. Sea level rising of the order of 100 meters will make a lot of people homeless. I think some estimates were 100 million. And where are they going to settle? And there's, I think, no proposed answer that has a chance at this time. Pardon me?
3 meters, not 100.
No, I'm sorry, I said that wrong. Sea level will rise 1 meter in 100 years, and that is enough to put many low-lying islands into great difficulty. The second job is to mitigate ice age that's going to happen in 5 to 10,000 years, not 5 to 10,000 years will be the time to the next ice age. And I wonder, I have no idea, but I wonder whether we can use what we've learned by our CO2 work in the atmosphere to actually mitigate the next coming ice age. No one has seriously thought about it. It will be very difficult because everyone in the world will have to collaborate. And besides, different nations will have different goals, and we have to find an agreement. Siberia may enjoy a warming that other parts of the world will not enjoy. Now, despite of the fact that the ocean plays a leading, crucial role in what's going to happen in the future, the word ocean did not appear in the United Nations Co-op agreements in Kyoto in 1997 and in Copenhagen in 2009. Very disturbing, because nobody wanted to mention the word ocean in connection with this obvious climate change. Then my last slide brought, curiously enough, a solution. No? We had a meeting in the Vatican, at the Vatican Academy of Sciences, under the leadership of Ramanathan, an oceanographer at Scripps, in 2014 on climate problems. The Pope being concerned that these will be most harmful to the poorest part of the world's population. The 3 billion people is what he estimated. But it was not a meeting of church people. It was largely a meeting of scientists, some very distinguished scientists. Lord Rees, former head of the Royal Society, attended, and other interesting people attended. Andy Revkin, who is science editor for the New York Times. And we had a very interesting 5 days there and walked away sort of inspired that there should be a chance to work together to find a common goal towards a sensible mitigation of the climate change. Another thing that happened is that the Dalai Lama, from an entirely different religion group, followed suit. And the various pronouncements of the Pope and the Dalai Lama led to a change in the last COP meeting in Paris in 2015, last year, which did in fact contain the words ocean. The preamble reads, noting the importance of all ecosystems, including oceans. Well, I don't think it was a great victory, but it's the beginning of an attempt to appreciate that we have to learn to understand the ocean better if we're going to do a sensible job of adaptation and climate mitigation. I want to remind you in closing that when we had the study of what to do about German submarines at the time of Pearl Harbor, that when everybody went to work together, we brought it to the landing in Normandy in 3.5 years. And that students looking for jobs before Pearl Harbor, the situation changed with jobs looking for students after Pearl Harbor. Now, none of us wish there should be a climatic equivalent of Pearl Harbor, but I think some things might happen that will make people more concerned, and if so, I would expect that any trained oceanographers will find plenty to do in worrying about the changing climate. It's a serious problem. Thank you. Okay.
Thank you very much. Thank you very much, Walter, for joining us and giving such a wonderful talk. I would like to also recognize Mrs. Mary Munk. Please get up.
Yes.
Mary, yeah. This presentation is a joint, as you could see the dynamic, is a joint production. So.
Yes.
Thank you. And now I would like to welcome to the stage Mr. Chris Mooney, an energy and environment journalist with the Washington Post, a highly regarded writer, public speaker, and science communicator. Mr. Mooney is known for commenting on the intersection between science and politics. He is the author of 4 books about science and climate change, and he received his degree in English from Yale University and was a Knight Fellow in Science Journalism at MIT. Chris Chris's coverage of climate change has surely elevated the issues in the public eye. He and Dr. Munk will explore some ideas and exchange thoughts on our oceans, climate and change, and the future. I will.
Can I sit over there? Oh, sure. Can I join you?
Please.
Okay. Okay. Hello. Nice to see you.
Nice to see you.
Did you know Andy Refkin?
I do know Andy Revkin.
Here's some
We're all part of the same little crowd. There aren't that many of us. So thank you for your fascinating talk, and it's an honor actually to get to interview you. I've seen your name so many times in so many papers that I've read, trying to understand them. And so it's great to actually talk to you. And there are many things that I could ask about, but I'm going to mainly focus on oceans and the climate system right now. There's so much happening. And I guess I'll ask you first, just generally, I think I reported that 90%, you correct me if I'm wrong, 90% of the heat that's being trapped due to climate change goes into the ocean. Is that correct?
Yes.
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 What does that mean?
It means it's bad news. It means even if, as we hope, optimistically, in 50 years, we could be carbon neutral. It's conceivable. We will end up with a different ocean than we had before, and you would naturally ask the question, how long would it take to get back to the previous situation? And the answer is that it depends on the time constant of ocean turbulent mixing, and the answer you get is more than 1,000 years. So unless we learn some new methods of collecting the carbon and storing it, it's going to be a long time.
What is your sense? Some people are saying, some scientists are saying that they're already seeing the big ocean change, which would be the overturning circulation change. And people are increasingly pointing to this big blue spot to the south of Greenland that's a cold anomaly, that's extra cold there, even as the rest of the globe is extra warm. And they're saying that sort of looks like this potential slowdown. I mean, what is your sense of that possibility?
I've heard of that, but I don't know enough about it to make a pronouncement.
Mm-hmm. But this is the big, the circulation would be the real ocean. In addition to sea level rise, it would be the big change.
And sea level rise, as you know, is sort of roughly 1/3 due to thermal expansion of the ocean, and 2/3 through to the melting of continental ice sheets. Mm-hmm. And the total contribution if Greenland melts is 9 meters to global sea level. And the total contribution if Antarctic melts is 100 meters.
You have spoken before, and you alluded to it briefly in this talk, about the science problem that involves Antarctica, which is these gigantic ice shelves.
Yeah.
Some of them are as big as a country,
yes.
Which create they're out across the surface of the ocean, so they create a cavity underneath it, so ice at the top, then filled with water. And you were saying that we don't really understand what happens down there, but that's where the melting would happen.
Yes.
What should we be doing about that?
Well, we should stop melting the ice sheet.
I thought you meant from more of a research perspective. Yeah.
Yeah. Well, I think there are possible ways, that you make us carbon neutral. That's a big problem, but I mean, if we should stop melting our ice sheets. Yeah. And the worry, is, at least for the polar ocean, that if the ocean itself gets warmer, the floating ice will disappear. That may happen quite soon, but it will also affect the continental ice on nearby Greenland, and that's a great concern. It's a very difficult problem.
Something I wrote on recently that your talk reminded me of was that as this happens, so this means the displacing of an amount of mass that most of us can't conceive of. Maybe you can conceive of it, but it's it's billions and billions of tons. And scientists at NASA reported that they can already measure that the wobble of the Earth has changed because of mass loss from Greenland and Antarctica. Does that make sense to you, that something like that?
I'm sorry, could you repeat
The Earth's
that?
wobble has changed.
Oh,
the pole
oh.
has moved because of the movement of ice off of the pole.
They would certainly respond to it.
Yeah.
It's a subject that interested me very much because it's a way of measuring the total mass distribution on the Earth. Whether it's a positive or negative feedback, I don't know. But it is true that if you melt, you change the rotation vector of the Earth, and that's a calculable feedback mechanism.
I also wanted to ask you about your remarks on ice ages and the fact that we are perhaps heading into one. I thought it was canceled. I thought that was what CO2 would effectively do, is even if the alignment of the planet might favor an ice age, if you have enough CO2, you can just sort of say go away, right?
If you have enough of it.
Yeah.
Yeah, that's the problem.
Yeah.
I think we have 5,000 years to learn enough, but I think of how to remove the next ice age. Do you think that that is the proper way for humanity to persist, to essentially eliminate the perturbation of the Earth's orbit from other planets by learning how to change the atmospheric thing? That is the challenge, and I think we have a lot to learn to do that intelligently.
We could overshoot. That's the thing.
We could overshoot.
Yes. And then it would take a long time.
Not we can overcome,
Right.
we can overshoot.
The oceans fascinate me, and I wanted to ask you about something else that is, I think, close to your research on waves. I don't know if you're familiar with this research, but there's recently a lot of interest in ocean waves able to throw rocks onto land. So there's research showing that this massive Category 5 typhoon in the Philippines moved boulders that were over 100 tons when the storm surge came ashore. And there's research that says that in islands in Ireland, the Aran Islands, rocks move when big nor'easter storms basically come through and hit these islands. Is it plausible to think that waves are moving really large 100-ton boulders sometimes? Are they that powerful?
Yeah, if the waves are big enough,
Yeah.
they can do that. Yes, well, there's no question. But why is that so very important?
I think it's just a demonstration of the power of storm surges, which, yeah.
If you're moving towards suggesting that wave power can solve our energy problem, which is very severe,
Yeah.
I'm of the opinion that it cannot do so appreciably. That even with very optimistic use of solar power and wind power, that we still will need some additional sources of energy, like nuclear energy, very unpopular
Yeah.
at this time with many nationalities, but will be required to meet the world's energy needs, and that something has to be done to do it safely, and I think something can be done to have nuclear power plants that are safe and properly constructed.
You don't think, I guess what you're saying is that marine and hydrokinetic energy are just too far away to really add
I don't
to the
think
mix?
there is enough.
Oh, you don't think there is enough? Because people are trying this, but it's very far behind even wind and solar, is my understanding.
Yes.
But there's not a huge amount of energy in the ocean. We just can't get it, maybe. Can't tap into
Well,
it.
you have to identify where it comes from.
Yeah.
I think if you're going to say that waves will solve it, I think that calculations that have been made would indicate that it's difficult. And one thing it would do is to remove surfing beaches from avid surfers, and that's politically impossible.
So, you've had this, incredibly distinguished and long career doing ocean sciences, and your lecture explained how, at the very beginning of your career, it was heavily dominated naturally by world events, which meant that people in this field ended up working very quickly for the military because it was a wartime situation. Obviously, it's a very, very different situation now. So, what do you think young oceanographers today, your age, then, but now, what is the situation going to be like for them, with climate change being probably the most conspicuous?
I didn't quite understand your question. Can you repeat it?
Well, we've moved from a time when oceanographers were were drawn into the global military conflict to a time in which I guess they're drawn into the global climate problem.
Yeah.
So what does that mean for young students who are in this field?
Well, I hope that I hope that they will be available for working on the climate problem, where I think we desperately need help of all different kinds. And I hope that the government will do as it did in World War II, will make a major concerted effort all over the world to put oceanographers to work, to understand and predict, so that some solutions can be found, but it's going to be very, very difficult.
What, in addition to them being put to work conducting research, what other roles should they play? I mean, should they be out in front of the public trying to explain what's going on with the overturning circulation, predicting how much sea level rise we can get? What about explaining what a sverdrup is, which is very difficult for anyone to understand, things like that?
Well, I think the nice thing is that different students, different people have different interests. There's some, like myself really, who has stayed close to the science problem, the understanding problem, although I've recently had the contact with the Vatican, and others who like to work to spread the information. And there ought to be a chance for a broad array of people with a broad array of talents to be part of the global effort.
Well, let me just ask you one last question. So I believe that on this campus we're celebrating Earth Month, is that correct?
I'm sorry?
They're celebrating, well, we just had Earth Day, but they're celebrating research in the Arctic this month and also.
Yes.
So what is your final outlook? I mean, you said that climate change is a huge problem. You're not sure if we're going to put off the ice age or not. I mean, do you feel hopeful, at least for the potential for research? Do you feel very worried? What is your, when you stop and think about this, how do you end up feeling?
Well, I remember what happened when we were losing the war at the beginning of World War II. And when people said, let's get together and find a way to solve the German submarine problem, the country was not uniformly in favor of the Allied effort. There were some very active German sympathizers. There was some confusion and opposition. And once everybody, after Pearl Harbor, that essentially ended. Everybody said, we have a job to do. And I was amazed that in 3.5 years, we could turn the world from a losing situation, because we were losing, to a winning situation. And so staying with me is the memory that when a broad group of people work together, there's very little you cannot do.
Well, thank you. It's great to end on a hopeful note.
Thank you.
I think people are probably very glad to hear that these days. They get a lot of grim news, so I think it's good to hear a hopeful note.
Thank you.
Thank you very much. Thank you, Chris, and thank you, Walter, for a great discussion and presentation. Now, from what I hear tonight is that the future needs a lot of students and scientists to work in this area. So this is hopefully something that our university, among other universities, can provide. And now, as we conclude this evening, I want to thank you for attending, all the audience for attending, and I'd like to say that there's refreshments in the lobby, and for people who would like to meet Professor Munk, please step forward, and we are going to be on the stage for a few minutes. So again, thank you again for such a great evening at the University of Delaware.